Hello. So this time we're going to talk about some of the basic of magnetics. So magnetics are used in power engineering a lot, from transformers to motors and generators and inductors and all that. So we need to go over the basics of magnetics to do this. So first of all, we start with Ampere's law. Which is the integral around a closed loop line of H dot dl equals the sum of the enclosed current. Okay, so now with this one, to really be able to do this line integral, we really need the magnetic field to be constant around the loop. Okay, so typically to do this, we always start with nice uniform geometries. So the two geometries that we end up using is here is a solenoid. And so basically it has just these wrappings around either air or some magnetic bar. And then we have a toroid, which is again the wrappings of the wire around some cylinder like this. Okay. So these are the two most common ones that we could do because we're going to assume that the magnetic field is going to be constant inside this region. And then we know that our loop is either going to be a circle for this one or just a simple line for that one. Okay, so let's look at Ampere's law for these two basic structures. Okay, so let's start with the solenoid. So with the solenoid, we have our magnetic bar in the middle here, and then we can see that I'm going to have these wrappings that are going to go around, and we're just going to draw them like this. And then you see we had kind of our bar that kind of wrapped around like this. And so what's going to happen is that the wire when we cut it, so we're basically going to be taking this solenoid and cutting it with the plane going through. So what's going to happen is that the wires are going to come up on one side. The X means going in and a dot means coming out. And so what we see here is that my magnetic field goes in one side and out the other side when we have this plane. So then I can come in here and I can make a surface that looks like that. So what we're going to do is we're going to say that this part here is a long ways away, so I only have the part going through there. And we're going to assume that my magnetic field is constant everywhere in this high permeability material. So then we're going to do Ampere's law around the surface. And so what we have is this H dot dl is going to be broken up into these different regions. So first of all, this region in here, we're going to assume that my magnetic field is in the same direction as my line. So this is just going to be some h value, we'll just call it h0, okay, times dx, and then we're integrating that from 0 to the length. And then we have these two side pieces, and in these two side pieces, my magnetic field is going to be perpendicular. So that's going to be 0 for one side, 0 for the other side. And then this one here, we're going to assume this is a long ways away. So this one's going to be 0 also. Okay. So then we have H0 times L is equal to the number of turns that I crossed inside my loop, which is going to be N times the current going through it. And so we see that H0 is equal to Ni divided by the length of my solenoid. So this is the magnetic field of my solenoid. And if we want to do it in vector form, it's going to be H0 x hat. Okay, so now we have our toroid. We're going to do the same thing for the toroid. So we have some circle, and it's this high magnetic material around this circle. And then we're going to have the set of red. So we're going to have these windings that we're going to be cutting. And then for every one, you're going to have a winding on the other side. Okay, and then it's going to come out on one side and go in on the other. So all these are kind of coming out and all of these are going in, or vice versa, depending on which way it's wound. And so now what we're going to do is we're going to take our surface to be just inside that, because my magnetic field is going to flow around there. And so then when we have our H dot dl equal to n times I. So now my h is going to be constant anywhere in there. So this is going to be h0 times the total length, which is going to be 2 pi r, where you see this value right here is the radius of my solenoid, which is equal to n times I. Now, the interesting thing is, well, if my magnetic field is constant everywhere inside of there, well, do I use the middle or this side or that side? Now, for these to work, they're all kind of approximate, so it shouldn't matter which one you do. We always take it to be the one right in the middle. Okay, so now my H0 is going to be n times I divided by 2 pi r. And then that is my magnetic field for a toroid. Okay, so now that we have the magnetic field in this region, now our next step is, so that's to find H. Okay, our next step is we're going to convert from magnetic field to magnetic flux density. Okay, so we are going to have B, which is my magnetic flux density, is equal to U times H. So what is B, which is my magnetic flux density? So what we have is magnetics get this plot that is H as a function of B. And this is called my magnetization curve. Okay, and so typically what it looks like is we get a plot. Okay, I don't know why it keeps messing up when I touch it. Okay, and then when we come down like this. So there's a couple things that we see here, and the one is we get hysteresis. So the way that we go up is a different path than the one we go down. We also get a saturation where this gets to be flat, which means that my H can increase without increasing my B. And then down here, the same thing, I can get the saturation the other way. Okay, now the slope right here, the slope of that line is linear. So lots of times we approximate it as being linear. Okay, and if we approximate it as being linear, then this becomes a constant. Okay, so first of all, let's talk about this saturation point. So what ends up happening is that a magnetic material is built up of a bunch of these little magnets, which are called little domains. And what happens is as you apply a magnetic field across there, all these magnetic domains are going to align. When all of them are aligned, then increasing the strength of this magnetic field can't align anymore. and that's going to be my saturation effect. And so how easy it is to align these domains is your um, permeability, which is that mu. Okay. The other thing is that whether I'm going up or down tends to be a little bit different, and this is called hysteresis. Now, in this, we're typically going to be using materials that we're going to be assuming that it's fairly linear in this region, and then we're going to look at our saturation at the ends. Okay. Now okay, so then keeping going, so then basically in order to get B, we just multiply it times this constant, which we're going to call mu. And we have a mu R and a mu naught. So B is equal to mu R times mu naught times H. Okay, so this is where we found B. Okay, so now we are going to look at the concept of flux. So my flux is equal to B times some area. So let's look at a solenoid first. So if I have a solenoid, you see, and then it has these wrappings that are going around, which we are going to draw those again as these wires. Okay, so these wires produce a magnetic field in here, right? So that has some magnetic field in there, and the magnetic field gets multiplied by mu to get B. And then what we want to do is we want to calculate that flux. So I'm going to take a cross section through here, and you see, let's assume that this is a circular bar. So this circular bar is going to have some area. So in this case, I'm just going to multiply my B times the cross-sectional area that's perpendicular to my magnetic field, and that gives me my flux. Okay, so we now have found our flux. Okay, so now we are getting into the concept of flux linkage. So that is called lambda, which is equal to the number of turns, and lots of times we like to use the capital phi for that. So this is my flux linkage, so I'm just going to multiply the flux by my number of turns to get my flux linkage. Okay, so now we found our flux linkage. Okay, so now we're ready to do inductance. So then my inductance is, my flux linkage is equal to my inductance times my current. Okay, so remember that the current produced my magnetic field, and then the magnetic field produced my magnetic flux, and then that around to get my flux linkage. So then if I want to get my inductance, I'm basically just taking my linkage divided by my current. So now we have found our inductance. Okay, so now let's kind of loop all of this back around into a big loop on this calculation. Okay, so we're going to start with our current. Okay, and so the current is going to produce my magnetic field. Okay, and so typically this is done by multiplying it times n over my length. Okay, and then we are going to change that into my b, and I do that by multiplying by mu. And then from there, I am going to change that into my flux by multiplying it times my area. And then I'm going to take my flux and convert that into my flux linkage by multiplying that by n. And then you see I'm going to divide by my current to get my inductance. Okay, so let's put all this together. So now L is equal to lambda over my current which is equal to, we're going to combine all those pieces together, L divided by the length times mu r mu naught times the area times my n divided by, and then I'm taking the I out because the I got multiplied times all of that. So then that is going to be my inductance. Okay, so let's look at it for a solenoid. Okay, so my inductance is going to be my number of turns squared times mu r times mu naught, which we use 4 pi times 10 to the minus 7, times, okay, so then here is my solenoid bar, okay? And my solenoid bar is going to have a radius of r. So now I need to get my area. So my area is pi r squared. Okay, and so that is going to be my, and then I'm dividing that whole thing by my length, which is this length here. So I divide that by L, and that is, well, we usually use lowercase l because we use big L for my inductance. Okay, so then this is my whole structure, and this is my inductance for a solenoid. And then if I want to finish it off, the toroid. Okay, now remember my toroid looks like this, and it has a big R like that. And then if I take the cross-sectional area there, you see that's going to be a circle, and that's going to have a little radius of R. So let's go back up to here. So we're going to start with N divided by my length. And so my length is the part that goes around here. So my length is going to be 2 pi times big R. I'm going to multiply that times mu naught times mu R. And then my mu naught is 4 times 10 to the minus 7th. Okay, so now I'm in the B. Now I'm going to multiply it times my area. Now my area is pi little r squared. And then I'm at my flux, and then I multiply it by N. Okay, and then I divided out my current, and so everything works out. And so then we put all this together. Now my inductance is equal to N squared mu R 4 pi times 10 to the minus 7 divided by the pi's cancel, and then we have little r squared over 2 big R. Okay, and then that is my inductance for a toroid. This is my inductance for a solenoid.